What's up, everyone? I'm Harpreet Sahota, hacker in residence at Voxel 51. I'm continuing on this series where I'm going deep into papers that were accepted into CVPR 2024. And if you're going to be at CVPR in Seattle, Washington, come by the Voxel 51 booth. Say hi. I'll hook you up with some swag. I'm looking forward to meeting every one of you. Now, let's get into this paper. Today's paper is two things I usually don't think about in the same sentence. That's creepy, crawly insects and cutting-edge AI. However, it turns out that this combination is an important area of research to do work in, because if we can accurately identify insect species, we can improve agriculture, we can protect our crops, and we can ensure food security. The paper I'm going to talk about today aims to do just that. This paper is called Insect Foundation, a foundation model and a large-scale 1 million data set for visual insect understanding. And this is buzzing into the world of precision agriculture, tackling the need for accurate insect detection and classification. The main contributions of this paper is a novel data set called Insect 1M, as well as the Insect Foundation model. Before getting into the paper, let's talk about the problem that this paper is trying to solve. In precision agriculture, accurately identifying and classifying insects is absolutely important. It's critical for maintaining crop health and ensuring high quality yields. But existing methods face several challenges. For example, current insect datasets are significantly smaller and less diverse than needed. For instance, many datasets contain only tens of thousands of images and cover a limited number of species. Given the estimated 5.5 million insect species, this is inadequate. This is going to lead to models that don't generalize well, and we're not going to have enough coverage for practical applications. Existing datasets also fail to provide the fine-grained details for distinguishing similar insect species. Many datasets lack multiple images per species, diverse angles, or high-resolution images that can capture the subtle distinguishing features of these creepy crawly bugs. This makes it difficult for models to differentiate between species that have minor but critical differences and variations. Many datasets don't have a comprehensive taxonomic hierarchy or detailed descriptions about the insects that are in them. They often provide very basic labels without any deeper taxonomic content, such as the genus or family levels. This again is going to limit any model's ability to learn effectively. The authors propose a solution to this with two main contributions: the Insect 1M dataset and a new Insect Foundation model. The Insect 1M dataset is actually just a little over 1 million images, and it spans 34,212 species, which is much larger than existing datasets. It also has hierarchical taxonomic information, so the subphylum, the class, order, family, genus, species, as well as auxiliary, how do you say that? Auxiliary levels like subclass, suborder, and subfamily. This also gives you detailed descriptions for each insect so that we're able to train models that can really understand what is in that dataset. In addition to this, they developed the Insect Foundation model, and this is designed to overcome this fine-grained insect classification and detection challenges, and it has several components to it. One is image patching. And with image patching, there's the patch extraction portion where input images are divided into smaller patches, which is going to allow a model to focus on localized regions of the image. There's also the patch pool creation. These patches are going to form a pool that the model uses for further downstream processing. They also come up with something called patch-wise relevant attention. This is a novel thing that they developed in this paper. The components of this is the relevance scoring and attention weights. So relevance scoring, this is where each patch is going to be assigned a relevance score based on its importance for classification. And you do this by comparing patches to masked images, and you're highlighting subtle differences between these patches. For the attention weights, the patches that have higher relevance scores are going to be given more attention, and this is going to guide the model to focus on those really relevant features of an image. Another part of this foundation model is the attention pooling module. So here we're doing feature extraction and aggregation of information. So for the part about aggregating information, the attention pooling module is going to aggregate information from the patches. It's going to use attention weights to prioritize the most relevant features. In feature extraction, it's going to extract detailed and accurate features so that we're able to distinguish similar insect species. Now we put all these together and we end up with this Insect Foundation model, and a really important part of this is the description consistency loss. And so the model incorporates this description consistency loss, which is going to align visual features that are extracted from the patches with text descriptions of the insects. So here we have a text decoder. So the role that the text decoder plays in this model is for feature extraction and alignment with visual features. The text decoder is going to extract semantic features from the textual descriptions, and then these features are going to encapsulate the essential information that's conveyed in the descriptions. The alignment with visual features. This is where the extracted textual features will be aligned with the visual features obtained from the image patches. And this alignment is going to happen through the attention mechanism. That way, the model is going to learn to associate specific visual patterns with the corresponding textual descriptions. The model also has this multimodal text decoder, and the multimodal text decoder is going to create a joint representation that's going to combine the visual and text features. So by integrating the visual and text data, the multimodal text decoder is going to enhance the model's contextual understanding. This is going to allow the model just to make better inferences during classification and detection. The entire model is trained in a self-supervised learning framework where the model is going to learn from data without really requiring any manual annotations for every single feature. The model is also fine-tuned using label data so that we're able to improve the accuracy and performance of the model. As a result, this new method was evaluated against current benchmarks for insect-related tasks, and the proposed model achieves state-of-the-art performance and outperforms existing methods. So, to sum it all up, key contributions to this paper is the Insect 1M dataset. It's a large-scale detailed dataset that has hierarchical taxonomic labels and descriptions. There's also the Insect Foundation model. This is using patch-wise relevant attention with the description consistency loss. Put this together and you get superior performance in insect classification and detection tasks compared to the current state-of-the-art. The work the authors did here is super important. It's going to really advance visual insect understanding. The contents of the dataset might be small, but the impact is huge. Shout out to the authors for doing this. I'm looking forward to hopefully meeting you guys at CVPR. I'll see you in the next one. Cheers.